I'm Tiffany Bao. Very pleased to be here to talk about our work, ByteWeight, learning to recognize functions in binary code. This is joint work with Jonathan Burket, Maverick, Rafael Turner, and David Brumley. We are from Carnegie Mellon University. So there are many kinds of binary analysis in the world. For example, malware analysis, vulnerability signature generation, decompiler, binary reviews, control flow integrity, etc., etc. Many of them need function information. For example, the compiler USENIX, which is published last year in USENIX security conference, needs function start to decompile and construct the control flow graph for each function. However, such function information can be removed by binary stripping, which means essentially function as well as other symbols can be discarded. Strip binaries are very common, especially for those delivered to public. So, without function information, analysis such like decompiler or binary level control flow integrity may not be work anymore. Our question is, can we automatically and accurately recover function information from strip binaries? We need to be automatic to meet scalability requirements. And also, we want it to be accurate because inaccurate function identification may affect downstream binary analysis. We begin our discussion by giving a simple example. So suppose we have a strip binary, and the source code is shown in the screen. We have two functions, fac and main, and basically it calculates a numbers factorial. So we want to find these two functions from a strip binary. And a simple method is to find those function prolog and match with the strip binary. Well, if the binary is compiled by GCC, under -0, which is the default setting, we can get these two functions. We are very happy. However, if this binary still compiled by GCC, but under -01, we cannot find the function fac. And if we compile it under -02, we will falsely identify function main. We also look for answers from the current industry solution IDA. We compile another example, which is essentially a calculator by GCC-03, and we found IDA failed to identify all these three calculation functions. And especially, IDA failed to identify function assign, which is a vulnerable one that you can exploit by buffer overflow. So, in fact, later on, we will see that IDA actually failed to identify and falsely identify a large number of functions. And this led us to investigate the function identification problem. So, in this work, we consider three variants of this problem. The first variant is function start identification problem, which aims to output a list of function start addresses. And the second one is function boundary identification problem, which is given a strip binary, return a list of function start and end pairs. Finally, we define function identification problem, which is given a strip binary still, return a list of function as sets of instruction address. We also propose ByteWeight, which is a machine learning and program analysis approach to function identification. We have training and usage. So to address function start identification, we first create a model of function start patterns using supervised machine learning, and then we use this trained model to match function start on strip binaries. Then we use program analysis to identify all bytes associated with the function, and then we get the function identification result. And finally, we extract the minimum and the maximum of the identified function, and thus we get function boundary. We start the function identification problem by firstly talking about function start identification. The machine learning approach towards function start identification is firstly proposed by Rosenblum et al. Their basic method is to firstly extract those most representative instructions, which they call as idioms, that can either occur at function start or followed by a function start. Then they learn idiom parameters, and in testing, they score each byte of test binaries with a combination of those parameters from matched idioms. The main issue of the approach is actually scalability. So according to their paper, feature selection, which is one step in training, costs for all 3 data sets consumes over 150 compute days of machine computation. This is a big overhead for training. So we propose ByteWeight. It is a lighter and also linear method to address function identification problems. The red squares shows function start identification, which is composed as training and classification 2 steps. And the blue parts means function identification problem, and the green parts, the final parts, represent function boundary identification problem. In training, our first step is to extract all k or less length sequences. The learning data is those N3 binaries, so we know the function start for those trained binaries. So given a binary, we will either extract the first k byte sequences or the k or less instruction sequences. The second part is to weight those extracted sequences. So for each sequence, we get its corresponding bytes and then count the times of occurrence for this byte to be a function start or not a function start. So suppose we have push RBP, its byte is hex 55. We have 2 times as a real function start and another 2 times as not a function start. So we score it using these 2 numbers, and we score it as 0.5. Another example is the sequence push RBP followed by move RSP RBP. So we found that they happens for twice, and both of this occurrence are function start. So we score it as 1.0. After weighting sequence, we can obtain a list of those extracted sequences along with their weight. So to store it, we generate a weighted prefix tree. In this tree, each node represents an instruction showing in the sequence. And then we weight those nodes according to our extracted sequence weight. For example, we have push RBP along with score 0.5, so we assign the node push RBP weight as 0.5. And also, for the next node of push RBP is move RSP to RBP, we assign a weight as 1.0. In classification, we score a test byte according to the tree and label it to be a function start if the score is larger than a default threshold. For each test byte, we disassemble at this byte and find the longest path in the tree that matches this assembly. For example, if we have this red 55, we want to score this byte. We first disassemble it, and we found push RBP can be matched. And then we continue, we disassemble the following byte, and we find move RSP RBP can be matched. Finally, we try to disassemble one more instruction. We found either of the nodes can be matched. So we assign 55 a score as 1.0. Another example is the second hex 55 happens in test binary. So we found that push RBP is the longest path to be matched. So we assign it as 0.5. And then we filter those bytes using a threshold 0.5. We find that the first hex 55 is the function start according to our default threshold. Interestingly, if we disassemble one more instruction of the first hex 55, we can get sub hex 60 to register RSP, which is very similar as the next node of the tree. All of them are doing stack offset subtraction. In general, the actual value of offset is not important because different functions can have different stack size. So in order to match different offset in testing, we have to make it same in training. So it makes more sense for us to generalize the offset to any positive number. Also, similarly, it makes sense to normalize jump instruction or call instruction by generalizing the target address to any address. We call this step as normalization. So this is an optimal steps for function start training. Below is how we address function start identification. And next, we're going to talk about function boundary identification and function identification. Function identification is based on function start identification. So we assume that we already have the function start result by classification. So given a function start, we firstly run CFG recovery, and we run RFCR, which means recursive function call resolution. For control flow graph recovery, we recursive disassembly, and we're using value set analysis to resolve indirect jumps. And then we have recursive function call resolution. Basically, is to add any card target as function start back to our identified function start set. So we will do this iteratively until stable. The program analysis part is based on Carnegie Mellon University binary analysis platform, which is BAP, 0.7 version. So after we finish function identification step, we will then extract the minimum and the maximum address for those identified function instructions, and then we get the function boundary result. So now let's talk about our experiment result. We first compare ByteWeight against Rosenblum et al.'s work regarding training performance. So in ByteWeight, we applied 10-fold cross-validation to 2,200 binaries. We spent 6.1 days to train from all platforms and all compilers, including logging. For Rosenblum's work, they didn't report the overall training performance, but they reported that for feature selection, they spent 150 compute days. So because their training data and code is not available from our knowledge, we would like to test it in the furthermore if we can access their code. Also, we compare precision and recall against Rosenblum and the rest of other binary analysis tools. So we have precision, we have recall. If the precision is high, it means we can more accurately identify those functions. And if the recall is high, it means that we miss less functions. We first compare our result with Rosenblum et al.'s work regarding function start identification. The blue bar means Rosenblum's work, and the orange bar means our work. We have three variants in this case. We have ByteWeight k equals to 3, which means we extract the 3 or less sequences. And we have ByteWeight no norm, which means ByteWeight without normalization. And finally, we have a full implementation of ByteWeight. The result shows that ByteWeight wins Rosenblum's work in precision and recall in our experiment test suite. Also, we compare our result against existing binary analysis tools. We compare ByteWeight against a naive method, which is basically just push EBP, move EBP, ESP using this function prolog. And we compare our result against the Dyninst, IDA, BAP, and we have two variants of ByteWeight, which is ByteWeight without recursive function call resolution and a full implementation of ByteWeight. Some bar is 0 here because the tool doesn't support the architecture. So from the experiment result, we can see ByteWeight wins in ELF binaries, and also ByteWeight has a comparable result against the IDA in PE binaries. We also compare function boundary identification result against those existing binary analysis tools. So it turns out that ByteWeight still wins in ELF binaries and have a comparable result with IDA in PE binaries. In summary, in our project, we propose ByteWeight, which is a machine learning-based approach. We create a model of function start patterns using supervised machine learning. And we match this model on new samples to find function start. Then we use program analysis to identify all bytes associated with the function, and ByteWeight is faster and more accurate than previous work. Finally, we have uploaded our experiment virtual machine at the following URL. So please feel free to download it and play with ByteWeight. At this moment, I will be very happy to take any questions. Thank you.
Please state your name.
Hello, Andrei Kostin, Eurocom. Thank you for the nice work.
Thank you.
Is there any particular reasons besides BAP limited platform support for not using intermediate representation such as LLVM to do this so that you would support any generic architecture like ARM or MIPS in the future? Thank you.
Thank you, yeah. This is a good question. So yes, in general, our method can be applicable for different architecture like ARM. So the reason why we're currently using BAP is our current implementation is based on this platform, and in the future we will embed this implementation into BAP. So that's the reason why we currently use it. But yes, I agree, there's nothing stop us from using some other tools to have a more general result. Thank you.
Hi, I'm Eric Eide from the University of Utah. This is a very interesting talk.
Thank you.
So from a quick scan of your paper, I understood that your results and your experiments are not compiler specific. So you had binaries that were compiled by different compilers. But do you have intuition about, I mean, if you if you trained it for a specific compiler, would your results be significantly different, better? Because in many forensic situations, say, you might have intuition about how the code was compiled. Okay, yeah, that's a great question. If you pardon me, I will just scroll back a little bit slide. So for Rosenblum's work, they are compiler specific, which means you need to tell them what binaries, like which compiler generated this binary. So this is our experiment we compare against the Rosenblum's work. And in this work, we use compiler specific knowledge. So basically, we have GCC compiled binaries, we have ICC compiled binaries, and they are both for ELF. Because Rosenblum's work currently just for ELF, the implementation that we get. So we divide into two groups according to the compiler information, and then we get our result. So if you can compare this result against the next slide, you can get the difference. And I believe the difference is not that huge. So for our method, we are open to different compiler. We don't need the compiler specification knowledge, and it still shows that the experiment result didn't change much. Thank you. Thank you.
Hi, Christian Russell, Saarland University. Thanks for the talk. It's really a nice, cool, generic method, I think, to find function products.
Thank you.
You know, I'm curious about the diversity of the prefix trees that you have found during the training phase. Can you tell me something about like how many products you found there?
Sorry, how many?
How many products you have found, like how many patterns?
Okay, yeah, that's a nice question.
So I will just scroll back to this slide. There was a prefix tree. It's better to indicate. So in our current result, so we trained on like 90% of those 2,200 binaries. So our current prefix tree contains thousands of nodes.
Okay, thanks.
Thank you. Any more questions?
Yeah, hello, Robert Gavlik, Ruhr University Bochum. Did you test also identifying functions in LLVM compiled binaries?
In our current implementation, no. And this is exactly the reason we want to open our code. So we are welcome for everyone to helping us testing on it.
Okay, thank you.
Thank you.
Let's thank the speaker again.